Alright, so for this equation, we'll be balancing C5H11OH, a liquid, plus O2 gas, yields CO2 gas, and H2O gas. So, of course, we'll start out by counting how many molecules of each element we have on each side. Oops, I actually like to match these up, so this will be our H, this will be O. Alright, so over here we can count, we have 5, 12, and 3. Over here, we have 1, 2, and O, 3. Alright. So, I'm going to start out right now by saying this H11 throws everything off a little bit, because 5 and 11, you gotta go really high, up to 55, to see how many times you can fit those two into each other evenly. But what I'm going to do here is I'm going to start right out timesing everything by 2. So we'll have 2C5, which is now 10. We're going to have 22 plus 1 is 23. Oops, 22 times 2 is 24. Sorry. And let's see, 2 times 4, 5, 6. Okay. Now, this looks a little easier to work with. We're going to go over here. I've got to get C to 10. So that's easy enough. We can just put 10 in front of C. 1 times 10 equals 10. That's 10 CO2. And now let's even our H's out. We have 24 over here. Need to get 2 to 24, so 2 times 12, which means we now put a 12 up here. This also changes our oxygens, of course. 10 times 2 is 20. We get 15 times 2 is 30. 31, 32. And over here, we have 10 times 2 is 20, plus 12 is 32. Alright, and our equation is now balanced. Sorry, that was a little bit confusing. I lost track for a second, but that is correct. I would just like to specify how I got a 15 here. What we did was we previously had 2O here, and this was regular O2, so it made it 6, or rather 4. What we wanted to do, because we knew we had to get the O over here up to 32 due to what we had to do to both the hydrogen and the carbon, I ended up putting a 15 because I knew the remaining 2 O's were already on this side. 15 times 2 is 30, plus 2 equals 32, which is how we balanced finally this equation. 2C5H11OH, liquid, plus 15O2 gas, yields 10 CO2 gas plus 12 H2O gas. Alright, so for problem number 2, we have if 115 grams of pentanol combusts in unlimited oxygen at a temperature of 75 degrees Celsius and a pressure of 1.05 atm, calculate the volume of the resultant CO2. What we want to do first is we want to convert the mass to moles. We do that by taking 115 grams of our pentanol C5H11OH times 1 mole of C5H11OH divided by 88.148 grams. And we want to then times that by 10 moles of CO2 divided by 2 moles of our pentanol. After that, of course, we get 6.523 moles C5H11OH. We then want to use our ideal gas law. In this scenario, we'll be using V equals nRT divided by P. That translates to 6.523 moles, which we got up here, times 8.314, which is the amount in moles, or rather our ideal gas constant, times 75 Celsius divided by 106.391 kPa, which is this, transferred into kPa, kilopascals. And this running through equals 38.231 liters CO2. Alright, so for number 3, if 115 grams of pentanol combust in unlimited oxygen at a temperature of 75 degrees Celsius and a pressure of 1.05 atm, calculate the volume of resultant water vapor. So our first step is to convert the mass of C5H11OH into moles, which is what we're working with. So I want to start out by taking the 115 grams of C5H11OH times 1 mole of that divided by 88.148 grams, which is the weight of this. We then times that by 12 moles H2O as we discussed in our balanced equation, divided by 2 moles C5H11O2 as discussed in the balanced equation. We'll then move on to step 2, the ideal gas law, taking V equals nRT divided by P, and of course this equals 7.828 moles. And moving down onto our ideal gas law, we want to take our answer from above times 8.314, the constant, times 75, the temperature, Celsius, all divided by 106.391 kPa, which is this, and equals 45.877 liters H2O, which is our answer. So, draw the Lewis dot structures for each molecule and determine the polarity of each. Starting with C5H11OH, the pentanol molecule, you can see with the polar force, or the more electronegative force, being oxygen, and the more positive force being H. You can see here in the O2 molecule, We got 2 bonds. It's non-polar because they equal each other out, meaning, yeah, there's no polar force. Next we have CO2, 1C with the 2 O's, also with 2 bonds. This molecule is also non-polar due to its linear shape, having charges cancel each other out. Lastly, we have H2O, seen to the right. This molecule is in fact polar due to the electronegative oxygen atoms pulling the H's in. So we see in total 2 polar molecules and 2 non-polar. So number 5, describe the types of intermolecular forces present in each type of the products. Our products are CO2 and H2O. CO2, the only intermolecular force in CO2 is dispersion forces, as both elements are nonmetals. And in H2O, it's kind of a special type, and it has dipole-dipole bonding, hydrogen bonding in liquid, and dispersion forces, resulting in all 3 types of dispersion, or intermolecular forces. So that's the difference between these 2. Alright, number 6. Based on what you know about the intermolecular forces of each of the products in the ideal gas law, which is a more accurate prediction of the actual volume of the final product, that of CO2 or of H2O? Now I said H2O. It would be the most accurate prediction of the actual volume based on the intermolecular forces that it has, resulting in dipole-dipole bonding, hydrogen bonding, and dispersion forces, and also for the reason that it's the most polar. It's the strongest molecule, whereas CO2 is non-polar. Yeah, H2O would be the most accurate prediction of the actual volume, as opposed to CO2. Alrighty, lastly, number 7. If the products are collected in a vessel that contains a small opening, which product will effuse at a faster rate? So the lighter the gas, the faster it will effuse, and the heavier the gas, the slower it will effuse. Whereas CO2 has a molar mass of 44.01 grams per mole, and H2O has a molar mass of 18.02 grams per mole. According to these rules, H2O would effuse fastest due to its smaller molar mass. Thanks for watching.